All right, let's jump into this deep dive. We're tackling first-order model theory today. Sounds a bit intimidating, I know, but it's really a fascinating area.
It is.
It's like peering into the heart of mathematical logic. What did you say?
Absolutely. It's all about using this super precise language to try and describe the universe, at least the mathematical universe.
So we're talking about formal descriptions and how they connect to the structures in mathematics.
Exactly. Think of it like a philosopher trying to figure out what reality really is.
Okay, I'm intrigued.
But instead of relying on, intuition or just observing the world around them, in model theory, we use logic, rigorous logic.
All right, so where do we even begin with building this formal language you're talking about? How do we describe these mathematical structures?
Well, the foundation is something called a signature.
Its signature.
Yeah, think of it as a toolbox, but instead of hammers and screwdrivers, it's filled with symbols. These symbols, they represent the fundamental building blocks of our mathematical world.
Okay, so like defining the vocabulary we'll use, right?
Exactly. If we're talking about, let's say, numbers, our signature might include the plus sign for addition, the times symbol for multiplication, the symbols for 0 and 1.
All the things we'd use to build sentences in our formal language.
Precisely. And with our signature in place, we can then create what we call first-order languages. And these languages, they let us create very specific formulas. Think of them as the building blocks of our formal descriptions.
But we need more than just symbols, right? I mean, how do we actually connect this language to actual concrete mathematical objects?
Right, and that's where the idea of a structure comes into play. A structure is essentially a set, a collection of objects, and we equip that set with interpretations for each of the symbols in our signature.
Hmm. Can you give me an example? I think that would help me understand this better.
Sure, think about the set of all real numbers, all those numbers on the number line.
Yeah.
We can turn that set into a structure. For example, let's take the symbol 0 from our signature. We interpret that as the actual number 0. The plus sign, that becomes the standard addition operation, and A becomes multiplication.
So we're giving real meaning to those abstract symbols, grounding them, so to speak.
Exactly. And every symbol gets its own interpretation. Like the symbol, we could interpret that as the usual less than relation between real numbers.
Okay, this is making more sense. We've got a signature to define our language, then a structure to give it all a concrete meaning. It's like having a blueprint for a building and then actually going out and constructing that building.
I like that analogy.
But how do we know if our formal descriptions, the sentences in our first-order language, are actually true within a given structure? How do we test them?
Well, that's where we get a bit more technical. There's something called Tarski's model theoretic truth definition. It provides this really rigorous way to determine if a sentence is actually true when we interpret it in a specific structure.
So it's like a truth test for our math statements.
Precisely. And it's really powerful because it lets us study these mathematical structures in an incredibly precise and systematic way, all using the tools of logic.
This is fascinating. But we're just getting started, right? I mean, where do we go from here?
Oh, we've got a lot more ground to cover. Now that we have the basic building blocks, the real fun begins when we start exploring how different structures relate to each other. So far we've been focused on single structures, kind of like a philosopher examining one concept all by itself.
Yeah.
But the exciting part is, well, it's exploring how different structures relate to each other. Those connections, that's where things get really interesting.
That makes sense. I mean, philosophers are always looking for connections between ideas,
Yeah.
trying to make it all fit together,
Right.
But how do we even begin to compare these abstract mathematical structures? They seem so different.
Well, we use these special kinds of maps called homomorphisms.
Homomorphism.
Yeah, think of a homomorphism as like a bridge between two structures. It's a function, but it's special because it preserves the relationships between the elements.
So it maintains the structure even if the elements themselves change.
Exactly. And the way it preserves those relationships, well, it has to do with the symbols in our signature. So let's say we have a homomorphism between two structures. Let's call them A and B. If there's a certain relationship that holds between some elements over in structure A, the same relationship has to hold between the corresponding elements in structure B.
An example would probably help me wrap my head around this.
Sure. Let's go back to the integers, the set of all whole numbers, positive, negative, and 0.
Right.
And we'll think about addition on the integers.
Yeah.
Now let's take the set of even integers.
Right.
We can have a homomorphism between those two structures. And one example, well, we could just double each integer.
A double.
Yeah, so 1 would map to 2, 2 would map to 4, and so on.
Oh, I see. So every integer gets sent to its double in the even integers.
Right, and notice what happens if we add 1 and 2 in the integers, we get 3. Now, if we add their corresponding elements, that's 2 and 4, over in the even integers, what do we get? We get 6.
Which is double 3.
Exactly. So the homomorphism, it keeps the addition operation intact, even though the actual numbers we're working with are different.
Okay, so the relationship, the addition is preserved. That's really neat.
It is. And now homomorphisms, they have some specialized versions. One important one is called an embedding.
Embedding.
Yeah, it's a homomorphism, but it's also one-to-one. It's like we're injecting one structure into another, but we're not collapsing any of the elements together.
So not only are the relationships preserved, but also the individual elements stay distinct.
You got it.
Okay. And I'm guessing there's an even more specialized type.
There is. If we have an embedding, but it goes both ways, that's called an isomorphism.
Isomorphism. So both structures are essentially identical.
Pretty much. They might have different labels, like different names for the elements, but the underlying structure is the same.
Like two editions of the same book, maybe different fonts or covers, but the content's the same.
Perfect analogy. Now, there's one more type of map that's super important in model theory. These are the elementary maps.
Okay, elementary maps.
And these are even more powerful than just regular homomorphisms because they preserve not just the basic structure, but also the truth of even more complex formulas.
So they're kind of like superpowered homomorphisms.
You could say that. It's like if a sentence is true in one structure and we have an elementary map between that structure and another one, that same sentence has to be true in the second structure as well. It's a very strong connection.
Wow. It's like having a translator that doesn't just convey the literal meaning of a sentence, but all the subtle nuances as well.
Yeah, that's a great way to think about it. And then we have elementary embeddings. An elementary embedding is an elementary map, but its domain is the entire first structure.
So every element in the first structure has a corresponding element in the second one.
Right. And it's important to remember that any elementary embedding has to be an embedding, but not every embedding is elementary.
That's tricky.
It is. And even if two structures are isomorphic, an embedding between them, it doesn't have to be elementary.
Really? Can you give me an example?
Let's go back to the integers and the even integers. Remember that embedding where we doubled everything?
Yeah.
That's definitely an embedding, but it's not elementary. And here's why. In the integers, there's no number you can add to itself and get 1.
Right.
But in the even integers, we can do that 1 + 1 = 2.
Ah, so even though both structures involve addition and they're isomorphic, that particular embedding doesn't capture everything we can say about them.
Exactly. And that's why elementary embeddings are so important. They give us this really tight connection where the structures are essentially indistinguishable when we look at them through the lens of first-order sentences.
Okay, I think I'm starting to get a feel for how these maps work. It's like we're comparing the inner workings of different mathematical worlds.
Yeah, that's a good way to put it. And these maps, they're just the tip of the iceberg in model theory.
Well, before we get too lost in the iceberg, maybe it's time to talk about those big theorems, the ones you mentioned earlier.
Absolutely. These theorems are kind of like the pillars that hold up the entire field.
So we've got these grand theorems, kind of like a foundation for the whole field of model theory.
That's right. They give us this incredible power to understand and manipulate structures in all sorts of interesting ways.
Okay, well, let's hear about them. What are these pillars of wisdom?
Okay, the first one we have to talk about is the compactness theorem.
Compactness theorem. All right, lay it on me.
It's a bit mind-bending, but incredibly powerful. It basically says that if you have a set of sentences and every finite subset of those sentences has a model, then the whole set of sentences has a model too.
Wait, so even if we have an infinite number of sentences?
Yeah, even then. As long as every finite chunk of those sentences has a model, the whole thing has to work out somehow.
That's pretty wild. So it's like if every piece of the puzzle fits together in small groups, then there must be a way to fit all the pieces together, even if it's a huge puzzle.
Exactly. And it has these surprising consequences. We can use the compactness theorem to prove that structures exist, even if we can't actually build them directly. It's like knowing a building exists because we have all the blueprints, even if we haven't seen it with our own eyes.
Okay, that's a pretty powerful tool to have in your logic toolbox. What's next?
Next up, we have the diagram lemma.
All right, the diagram lemma.
This one's all about capturing the basic facts about a structure. Like, imagine taking a snapshot of all the relationships between the elements. That's kind of what a diagram does.
So it's like a blueprint specifically for that one structure.
Exactly. And it tells us when we can stick one structure inside another one, technically speaking, when we can embed one structure into another.
Okay. So we're using diagrams to figure out how structures fit together. Makes sense.
Mhm.
What else have we got?
Next, we have the Linden interpolation theorem. This one's a bit more technical, but it's super useful. It's all about finding a kind of bridge between two descriptions that can't both be true at the same time.
A bridge.
Yeah, so let's say we have two sets of sentences and they contradict each other. The Linden interpolation theorem says there's this intermediate sentence that kind of captures what the two sets have in common, even though they disagree overall.
So it's like finding the common ground between two opposing arguments.
Yeah, that's a good way to think about it. And it has these deep connections to classical logic, like the laws of distribution for syllogisms. It's pretty cool stuff.
Okay, I'm starting to see how these theorems are all connected. Each one gives us a different perspective on how structures and sentences interact. What's next on our list?
We have the omitting types theorem. This one's all about finding structures where certain kinds of elements don't appear.
So, like excluding certain guests from our mathematical party.
Exactly. And the way we do this, well, it has to do with the idea of a type. Remember, a type is like a description of a potential element.
Right, it's like a profile of all the relationships that element would have.
Right. So the omitting types theorem tells us when we can find structures where certain types just don't show up, it's like saying, hey, I want a structure where no element has this particular set of relationships. And the theorem tells us if that's even possible.
Wow, so we can actually control what kinds of elements exist in their structures.
Yeah.
That's pretty neat. What's the last one?
The last one is the initial model theorem. This one's all about building structures that are minimal in a certain sense.
Minimal.
Yeah, like they only have the elements that are absolutely necessary to satisfy the basic rules of our theory. No extras.
So, kind of like building a house with only the essential rooms. No fancy guest rooms or home theaters, just the basics.
Exactly. And the initial model theorem tells us how to construct these minimal structures. It has all sorts of applications in computer science where you might want to specify the behavior of a system in the most concise way possible.
Okay, so those are the 5 big theorems of model theory. They seem incredibly powerful, but also really abstract.
They are abstract, but they have this amazing ability to capture the essence of how mathematical structures behave. And what's even more exciting is that these ideas are constantly evolving and finding connections to other areas of math like computer science, linguistics, and even philosophy.
It's like these tools from logic are helping us understand not just math, but language and knowledge itself.
Exactly. And who knows what other connections we might find in the future.
That's a great thought to end on. There's always more to explore, more connections to discover. Well, that's our deep dive into first-order model theory. Thanks for listening.